Well, hello. It's so nice to see so many of you here at 9 a.m. on the Tuesday morning after a night of cocktails and perhaps extended cocktails for some of you. Lovely to be back. I can just witter on until people begin to grab a seat. Close to the front, please. There's plenty of space today. I think people are a little bit late in joining, which is a shame because we have a really fabulous opening hour. And the opening hour is going to be on architectures for space economy. We've got three great speakers in this section. I'm just going to keep nattering on because I want as many people as possible to listen to these speakers. Welcome also to those who are still joining us online. And just for the course of today, as with yesterday, we will have many sessions in this room, of course, and then a number of parallel sessions happening downstairs in the delegates room, including one right now with Larry Kujko from ESRIC, and he's going to be, not that I'm encouraging you to go down there, but it will be wonderful as well. He's going to have a series of startups speaking, and it's going to be about the support program pitches there that ESRIC provide. So some really great startups down there as well. But here we've got, certainly I wouldn't really consider any of them startups anymore, but quite new companies. And we're going to start with OrbitFan. Started in 2018, opened its UK office in 2022, and that will be represented by Tejaswi Tiruvuru, who's going to talk about building a sustainable lunar economy, refueling and in-situ resource utilization. And because one of our first hour speakers has dropped out, we will have the time to hopefully have audience questions as well. So listen keenly, and Jazz, I know, is very happy to take questions. So please welcome her to the stage.
Hello. Can everyone hear me okay? Yep, amazing. Thank you, Lisa, for that introduction. And I'm very glad to be opening our Tuesday here. So as Lisa mentioned, I'll be talking about building a sustainable lunar economy. So refueling and in-situ resource utilization. So I'm Tiruvuru, and I'm the Business Development Manager at OrbitFab. So, a little bit about OrbitFab. As Lisa mentioned, we were founded in Silicon Valley in 2018, and our UK office was actually founded in 2022. So what we do is we do in-orbit refueling of satellites. So predominantly, across both companies, we've got around 60 full-time employees. We're headquartered in Colorado, and our UK office is based in Harwell, so just south of Oxford. We're actually backed by quite a few prominent investors, so two of which that I want to mention here, Lockheed Martin and Northrop Grumman. So the first ever time these two competitive aerospace primes have actually invested together in a company because they see strategic value in what we do. We've also had two successful spaceflight missions, which I'll talk about in my following slide. And this here that I brought with me, which was very fun to get through airport customs and security for the UK, but this is Rafty. So this is our interface. Now, if you've got Rafty on your satellite, then we'll be able to come, dock with you, and refuel you. So we're trying to make this industry standard. So it's already baseline in a number of, governmental and commercial missions. So as I mentioned, we were in the UK, founded in 2022, predominantly based here to grow the European capability that we see, in all these conferences, all the big companies that are coming up. So we've actually qualified Rafty for low pressure propellant, so LP Rafty, so that's for chemical propulsion, using hydrazine, things like that. In the UK, we're developing a pressure agnostic refueling system, which means developing a high-pressure RAFT which can do electric propulsion, green propellants, different propellant types, so that we can service more of the market. As well as our grappling interface, which is our active side called Grasp, which will grapple onto RAFT, and then we'll be able to come and refuel. We've also, won quite a few commercial and private institutional funding as well for green propellants. As I mentioned, we are based, headquartered in Colorado, and then that's our US office. Since sending this presentation, I say that we're a 15-person team, but again, we've grown. So I'd say that we're around 20 now. Just to give you guys a bit of background, a year and a half ago, I think we were at 6 people, and now we're at 20. So you can see that exponential growth that we've had, especially in our UK branch. We've got a lab space as well where we do rapid prototyping and testing of our interfaces, RAFT and Grasp. We're also looking at ESA and UKSA commercial contracts, as well as now looking into lunar and defense. So, a little bit about our company wins. So, in 2018, we were the first private company to resupply the ISS with water. So that is our FURPHY mission. You can see that's astronaut Christina Koch with 2 of our orbital test beds there, where she was demonstrating and sort of testing out the fluid dynamics of how fluids behave in zero gravity. We took the learnings from that mission and went to our second mission, which was Tenzing, which is from 2020 to 2021, which is a depot which has RAFT on it that's actually currently orbiting LEO. SSO. So we've got a depot up in space. And with that Tenzing mission as well, we actually performed an on-ground testing of RAFT to say that this can also be doubled as a fill and drain valve. So, every satellite has a fill and drain valve. Any space vehicle that has, a prop system will have a fill and drain valve. So if you've got RAFT in place of that, then we'll be able to come dock with you and refuel you. And then going on to the latter part, so 23, 24, we did some RPO test beds. That was mainly predominantly done in the US. And then in 25, so later this year and early next year, we are looking to actually launch our first fuel depot into GEO. And there, that will have a client, so the US DoD will come and actually do a self-service, which means they will come on, dock with us, and then have a refueling. So, Orbit Fab's ambition, what do we want to do? We want to build a bustling in-space economy. Now, how do we do that? So short term, what we do currently and what we're thinking to do in the short term is launching fuel from the Earth and then using that fuel to refuel, assets in space. It works now with our customer base that we've got. We can make fuel here and then launch up. Launch costs are relatively cheap. It's easy to do, I say. But it's inefficient. And when we're talking about sustainability, just thinking about how much, pollution is created when we're trying to make fuel or with launch, things like that. So we don't see this as, a future option. Then we go on to our medium-term goal. So once we've demonstrated that fueling capabilities in short term, we go on to the medium-term goal, which is essentially RAFT replacing fill and drain valves and to enable any spacecraft to be able to utilize our service. So we want to basically make this as a common interface for any space vehicle. Now, this enables transfer of not just fuel, but any sort of liquid that's required, and gas in that case as well. So, in terrestrial, whether it's, in orbit or on the moon or cislunar, anywhere, we want to be that logistics supply chain. It also removes the complexity, I guess, of having different interfaces. If you've just got this one that can double up as a fill and drain valve, do on-ground and also in space testing, it's kind of helpful. So we want to be able to offer that service at medium term. Now, the long-term goal is to actually produce that propellant in situ. And then sort of once it's produced in situ on the moon, for example, then we'll be able to transport it. We essentially want to be that delivery driver, that logistics supply chain. So it's a lot more, economic if we're using materials derived in space to be able to service other clients. And it also enables that bustling in-space economy. So going from Earth to the moon, and then from there being able to get refueled, for example, and doing further missions, either going to GEO or GTO or even Martian missions, for example. It's that next step of building that in-space propellant supply chain from materials derived in space. Oh, there you go. So this is actually a market analysis that I think maybe a couple of you will be familiar with. It's the PwC market report that they did on where they think the lunar economy is going. Now, I will say I think maybe these numbers might be a little bit outdated with the current climate, economically and politically. But reason being, I still do think, and I think we all here think, that there is a big, big market in lunar. And I feel that refueling underpins a lot of these different markets. For example, with commercial government missions, you've got your Artemis missions or your Moonlight mission, be able to FaceTime people from the moon. How cool is that? So all of those, what we want to do is be able to sort of be that supply chain, that logistics supply chain for loads of different, markets and companies. For example, mining. I think this is a speaker after me, but me and my manager were having a discussion about a company called Interlune, who have recently found, helium-3, I think, on the moon, which incredible, but that's a resource, for example, that could be utilized on the Earth. So again, building that, being able to deliver that, things like that, that's what we want to be involved in. And as I mentioned, also ISRU, something that we also, will underpin our success. So where are we in terms of Orbit Fab? So the ticks there represent things that we've already done. So as I mentioned, demonstrating resupply of water, that's our FERFI mission, our Tenzing mission, which is launching our depot into SSO, and then qualifying RAFTI for low pressure liquids. Now, what's currently in development is launching that orbital depot to GEO, which is going to happen, as I mentioned, towards the end of this year, early next year. Qualifying RAFTI for high-pressure gases, so as I mentioned, for green propellants, xenon, krypton, things like that, for electric propulsion. And then demo this docking and resupply, so actually demonstrate it in space. Now, what's next for Orbit Fab is to do that demonstration of high pressure as well in LEO. So not just low pressure, not just chemical propulsion, but also for electric propulsion. And then on our lunar roadmap, what we want to do is qualify this interface. So this is our RAFTI, but then also our GRASP, which is the active side. Qualify this interface for the lunar environment. So, being able to perform in a similar way where the conditions are completely different, with lunar dust, with, for example, gravity, things like that. Then integrate RAFTI onto different lunar and cislunar platforms, and then also demonstrate that fluid transfer in the lunar environment, and then going further and doing that robotics and resupply on the moon. All of this, what we want to do is we want to be capable of being, the most common or most liquid, most gases that are being utilized, feedstock, but being able to deliver that to people that require it anywhere on the moon or anywhere essentially in space. So the how are we going to do it? I'll put my technical hat on, I'll try my best here. But this is essentially our architecture, which is what we're actually hoping to develop with the Space Resources Accelerator, which we were grateful enough to have won last year as well, so we're one of the companies there. So on the right over there, you've got our RAFTI. So that can be any platform, any system on the moon, for example. So it could be a rover, it could be anything, it could be a lunar transporter, for example. If you have RAFTI on your prop tank, then it gives you that architecture, it gives you that ability to be refueled, which is what we do here on the left. My left? My left, your right. When you've got GRASP, and then you've got that robotic system to automate that fluid transfer. So just to sum up there, Orbit Fab's ambition, so we want to be able to essentially do lunar, so essentially perform our interfaces, do our interfaces on the moon. So make sure that, do regolith processing, which is getting rid of the moon dust, being able to demonstrate that our interfaces still work, and then being a supplier and transporter of the key gases and liquids as well that companies will require, and then help Europe build that ISRU value chain. And over there, on the left, we've got some companies, potential partner organizations that could be interested in what we do as well. But thank you very much, and I'd always like to end on that quote. I'm sure everyone here knows who that astronaut is, but just remember, if I had one choice, I would always take more fuel. We have that at the end of every presentation, and even on our emails, just to remember why we're all here. But thank you very much.
Thank you, Jazz. Thank you so much. Thank you for starting the morning. Oh, no, we may have some questions. Oh, we already have a question. His hand is very... We have a couple of questions already. Three hands, all on this side of the room. Let's start with Jerry. You're the first hand I saw.
Jerry Sanders, NASA. So, two kind of quick questions. One is, are you in control, when you dock...
Yes.
Do you control the client spacecraft valving, or do you have to coordinate that? And the second part of the question is, after you dock, how do you verify the seals before transfer?
I'll try my hardest to answer the second question, which is quite technical. But the first one, in terms of, yes, we would have a level of control, but it would, again, we would have to work with the client. So with Rafty, you need to make sure that there's, a keep-out zone. So there are little things in design that we need to make sure that we sort of build into the design with the customer. And then we would dock onto them, and then 2 active valve cores will go in, and then we've actually got some sealing as well to make sure that there's no liquid lost. But that, again, I'll take back to our engineers. They'll be able to give a better description.
Typically, between a fill and drain valve or a coupling, on your graphic you showed a tank and Rafty. There's usually valves between them to make sure. So who commands that valve between Rafty and your client's tank?
That would be us. So we've got active valve cores.
So you actually
that would be us, yes.
Okay.
Exactly.
Ben? Oh.
Hi there, Ben McEwen, UNSW in Sydney. A great talk. I actually went to visit you guys in Colorado last year and met with Daniel Faber, and what you're doing is fantastic.
Thank you.
You spoke a little bit about the market on the moon.
Yes.
Have you done much research in terms of the market size in orbit, refueling satellites? That's where you guys are going to be targeted firstly. So what sort of sense of market size can you give us?
Yeah, so in terms of market size, this is what I find quite interesting, obviously being BD, is the business cases are very different. So you've got LEO and you've got GEO. GEO, you've got more expensive assets over there. So a lot of operators want their assets to be refuelable because, it's expensive to launch there, keep them up there for longer, keep that revenue-generating asset there for longer. Now, with LEO, as I mentioned, it's pretty cheap to launch. You can get there, you can build constellations, you can just keep launching up there. That poses a second problem with debris. And that's where we come back to that sustainability angle. You can't keep launching. So there is that understanding where there are companies that they are thinking, there is that market there to be refueled in LEO as well. But there's also that other thing, it's closer to the Earth. So the Delta V operations with LEO is far more fuel intensive. So we get quite a few customers come to us and say they want to be able to maneuver with a lot of freedom. They don't want to think about fuel being an asset that's going to complete. So that's another way where we'd go and we'd refuel. So there are different business cases. You've got the geo market where you've got assets there for longer, more expensive, and there's a huge, huge market there. Contrary to popular belief, I believe that the geo market isn't dying. It might be declining because of how easy it's to launch to LEO, but the business cases are different in both. And then why stop there? Obviously, you've got the Martian missions going even further, which again require refueling.
Are you working with SpaceX?
I'm the UK branch. That might be a question for the US.
Thank you, Ben. Danon, and then Jun, and then we have a question here. So.
Hi, Data and Nicole, Carmen Plus. We're just down the road from Orbit Fab in Colorado, so thank you for your talk. Also a question on the market analysis. Your analysis of the lunar market in 2040, I was wondering if you could expand on the commercial government sector. I think you said it was something $50 to $90 billion. And I was wondering if you could talk a little bit more about the commercial market in particular, and if there's any distinction you see with direct contracting to government, indirect entities that are there because of that, and if there's any commercial market independent of that you guys see.
Yeah, I'd say, like I mentioned, quite a lot of those figures came from the PwC report that did the analysis on what the government and commercial missions are looking like. Predominantly, as we saw with government, there's you've got ESA, you've got a lot of other like national space agencies, JAXA, ISRO, going to the moon and doing that testing. There's also a commercial sample. I mean, we've not been to the moon in years now, absolutely years. So there is that benefit for quite a few companies that see that. We do see that commercial market also growing. In terms of, there are quite a few companies here as well that are sort of building that infrastructure to go to the moon. And that's where we come in. We want to make sure space tourism, for example, things like that, we want to make sure that this technology is there for everyone that needs it. You could be anywhere on the moon. We just want to be there to be able to sort of deliver this asset to them and be able to refuel them. So we see the market in both, essentially.
I'm going to take the next two questions quickly because we're at time. Okay. And if you have quick answers.
Okay, I'll try.
But I like to hear the questions because it shows the ideas in the room. Jun, and then the gentleman there.
Jun Schmel from JAXA. Could you give us a sense of a unit price for the fuel? Is it going to be like $100,000 or $1 million?
Yep, that would be a very quick answer.
Great.
So we've actually published our price for hydrazine in GEO per kilogram, which is 200,000, so 200K per kilogram dollars in GEO, and 75 in LEO, so 75K per dollars per kilogram in LEO.
Great, quick answer.
Yes.
Joe Hartwigson, Oxyon Energy in Salt Lake. Do you anticipate having different devices for different fluids, kind of like the Compressed Gas Association, so that you can't mix the wrong ones?
Yeah.
For example, we've run our solid oxide stack on hydrazine, nitrogen tetroxide, or surrogates. And if you were trying, as a fuel cell to generate power on orbit, if you're trying to refuel such a device and you cross them, it would be catastrophic. So I just wondered if there's different devices for different fluids planned.
Yeah, short answer, yes.
Great.
So, okay.
That's great.
Yes.
Short answer, yes, it can be taken. I don't want to take Gary's time away. Thank you very much.
No problem.
Thank you. Sorry, I really don't like cutting people off, but I just want to definitely not get on the wrong track of time this morning. And we have, as you mentioned, we do have Interlune here, and it's Gary live from Interlune, and he's going to talk about harvesting helium-3 from the moon. Thank you.
Good morning, everyone. Let me first tell you a little bit about Interlune. You might not have heard much about us. So we are a startup with a very big vision. We aim to be a world leader in harvesting natural resources from space to benefit humanity. We are not an ISRU company. Our primary focus right now is actually harvesting resources to bring them back to Earth, to supply Earth industry. All of our customers are Earth industrial customers. So while we're creating a space economy, it is essentially for export from space to Earth. We're based in Seattle, Washington. And we've been working quietly for a number of years, but we did emerge from stealth last year in March and are now talking more about what we're doing. We raised a seed round, and we're in the process of raising Series A, but to date, we've raised about $18 million US to fund our operations, but more importantly, we're also funded by various agencies, federal agencies, as well as the state of Texas. Department of Energy, in fact, is a key partner because they are one of the primary purchasers of our product in the world right now. Our grant from the Texas Space Commission will allow us to establish a regolith research center in the state of Texas. And today, I'm going to be talking about far future architectures, but most of our staff are actually working on technology development projects that are related to helium-3 harvesting. So let me tell you a little bit about helium-3. It is an extremely valuable resource. Today, the market price is anywhere from $20 to $25 million per kilogram. That is because it is a very useful resource and it is very rare on Earth. The entire quantity of supply on Earth is only measured in a few kilograms per year of production. It primarily comes from the decay of tritium in the nuclear weapons stockpile of the US and Russia. But it is relatively abundant on the moon because it is produced in fusion reactions on the sun. And the moon has no significant magnetosphere to deflect it, so it's been accumulating on the surface of the moon for billions of years. It is in use in two primary industries today, as well as some growth markets. So today it's used in border security. It is an excellent neutron detector, so helium-3 filled detectors are at major ports and borders in order to detect smuggled nuclear material crossing those borders. And the most exciting and emerging field is it is an essential ingredient in most quantum computing architectures, such as the ones you might have heard about from Google, Amazon, and Microsoft. It is used in a device called a dilution refrigerator. It is the only technique that's capable of getting to the low temperatures, millikelvin temperatures, that are required to run those quantum computers. So that is growing very fast. The current demand is well in excess of supply, and the world stockpile is decreasing. Obviously, there is also some upside industries, fusion being a huge upside, but I want to stress that we can make an operation or a business just on those two existing markets. We also have contracts, historic contracts that we recently announced. We have purchase agreements from the US Department of Energy, as well as Maybell Quantum, which makes dilution refrigerators. It is a precedent-setting contract to extract a resource from the moon, bring it back to Earth, and utilize it. Spatially, you've probably seen this before if you're in this field. Helium-3 is not evenly distributed around the moon. We have our own proprietary maps. This is a public map, but basically the high concentration areas by a factor of 10 are shown in the red. And they're primarily near-side equatorial. And you cannot detect helium-3 directly. You basically have to detect proxies for it, which are titanium and soil maturity. So that is how these maps were generated. But that does mean we're nowhere near the South Poles because there's no helium-3 around the poles, or very little of it. Our mission roadmap is multiple steps. We are preparing for our first lunar mission, a technology demonstration of one of our proxy sensors called Crescent Moon. That payload is ready. It will go on a rideshare on a lunar mission at the end of this year. Our next mission is Prospect Moon. It will be a small payload on a CLIP-scale lander. And I'll talk a little bit more about that later. But the rest, we have a roadmap. I'm also now going to talk about that initial operational capability, the architecture for that initial operational capability that we have used to work backwards to all of our technology development roadmaps. So what does a helium-3 operation look like on the moon, helium-3 harvesting operation? This had never been done before to any significant detail before we embarked on it. And this was our starting point. We have since been iterating on this, and over time, as we learn more from our prospecting missions, from our technology development, we will be maturing this architecture. First, to establish the general operating area based on the demand that our customers have told us that they need in approximately 2030. We've determined we can harvest and sell at the current market prices around 20 kilograms per year. It would be in a near-side equatorial region. The operating area is about 1.2 kilometers in radius, and that would support 5 years of operation. All of the equipment that we've architected, we believe, can be landed in a single Starship landing. It consists of three major elements: a harvester element, a power element, and a return element, which I'll be going into in more detail in the next slides. But the idea is that in the center, there is a field where the solar power infrastructure and wireless power transmission is located. And around that center are 5 fields, which are used to harvest the helium-3, each field occupied by one harvester, essentially running lines. The harvester would be a mobile platform. We continuously excavate to about 3 meters in depth. We have information from the Apollo core samples that there is helium-3 in the subsurface, not just the surface. And would excavate at a rate of 100 tons per hour. That's the rate you derive that you need based on efficiency factors and utilization factors that in order to get 20 kilograms per year or 4 kilograms per year for each harvester. On board, there is volatile gas extraction through mechanical processing, as well as isotopic separation systems. And so all 5 harvesters combined would produce about 20 kilograms per year, operating remotely. There's no humans on the surface in our architecture. Again, the stationary element, the power element, in terms of power requirements, each harvester needs about 40 kilowatts of continuous power during the lunar day. And to be transmitted wirelessly, given that by the time they're at the edge of the field, they're over 1 kilometer away. And so in order to do that with loss factors, we've derived we need to generate about 70 kilowatts of power per harvester, or 350 kilowatts for all 5. And then finally, the return element. We need to return product. The great thing about helium-3 is you don't have to return very much of it. So our baseline is to return 5 kilograms per launch, and to launch about 4 times per year. And that 5 kilograms, the actual payload mass is closer to 30 kilograms, because it would be in a pressure bottle at high pressure on the surface. And so we're launching essentially a small capsule that contains this pressure vessel, about 60 centimeters in diameter. In order to get that product into the return capsule, harvesters are periodically going to this return launch battery and offloading, or there is another small logistics rover that does the transfer. Okay, so that's what we believe in architecture looks like, at least as a starting point. So we went from that and worked backwards to what do we need to do today, because we don't anticipate launching and operating this for a number of years. There's a lot of steps to go, a lot of new technology that needs to be developed. The main thing I want to stress is that we do not intend to do this all ourselves. And we are looking for partners, we are looking for collaborators, we are looking to buy services that others are developing. But there will be core technology that we own, and that is the technology associated with helium-3 exclusively. And that is what we are developing in 4 steps. Excavation, sorting, extraction, and separation. So first, high-rate excavation. Nobody else will do excavation on the moon at the rate that we need to, 100 tons per hour. So we consider that to be a risk area. To that end, we have partnered with the Vermeer Corporation, which is a large surface mining and agricultural supplier in the United States. And with them, we have built a full-scale prototype of the excavator. It is capable of excavating at 100 tons per hour. We're testing it in the large regolith analog field and validating that we can hit the power consumption targets that we are after in our architecture. The next step is sorting. So something I didn't mention is that most of the helium-3 is in fine particles. It is not in coarse particles. So to reduce the amount of material we need to process, we use centrifugal size sorting to sieve the particles. We have developed a device to do that, funded by the National Science Foundation and flown it successfully in lunar gravity. Extraction, so another key part of a helium-3 architecture is the helium is pretty loosely held on the outer surface of the particles. It does not require heating in order to extract, but it does require crushing at very, very fast rates. So again, with multiple lunar gravity flights, we've been iterating on and perfecting a technique to mechanically crush and process in off-gas volatiles. And then finally, separation. So the off-gas that we get in volatiles is only a very small percentage is helium-3. So in order to reduce the amount we need to return, we need to isotopically separate that. So today, in our cryogenics lab in Seattle, we are routinely enriching helium-3 mixtures to very high purities by cooling them through cryogenic distillation to 2 degrees Kelvin. And then finally, I want to talk about Prospect Moon. So, I've talked about our future architecture. I've talked about our Crescent Moon first mission, but our first significant mission is this Prospect Moon mission. We want to use it to go to our future harvesting site. We have several candidate sites picked out. We're going to narrow that down and launch a mission in 2027 to a near site equatorial location we intend to harvest from. The objective of the mission is to develop, also through an orbital element, a high-resolution proxy map for helium-3. Today, the resolution is around 200 meters, and we want around 5 to 10 meters. And then to do ground truth, to measure the actual abundances of helium-3 there at that very high concentration region and do ground truth, proof of existence that it is there. We have multiple payloads on that: sample acquisition, mass spectrometry, a prototype of a regolith extraction device, multispectral imager. And we have, even after that, about 50 kilograms of payload left that we would love to share with anyone that wants to go to the site in the near equatorial region. So please, I'd love to talk to you if you're interested. In terms of status, we are on track for a PDR next month. Like I said, we've narrowed down to 4 candidate sites, and we have selected the lander as well as all of the payload partners and made initial payments, but we're not quite ready to announce that yet, any of those partners. And with that, I'm happy to take questions.
Thank you, Gary. Thank you very much indeed. So, the hands are the same 3 hands. Oh no, we've got another hand over here. Ben, I think we need to go this side first. I'll come back. Do you know, I'm so glad we lost a speaker this morning because already we're tight on time. Okay.
Hi, Will Coogan with Firefly Aerospace. Yesterday, I think a lot of us were excited to hear about the symbolic exchange of resources iSpace is hopefully doing next month. This is what you're describing, not symbolic. You have a customer who actually wants materials in hand here back on Earth. So I think it's hard to overstate how big of a deal that is. My question is on the supply and demand of helium-3. As you start bringing them back, that cost per kilogram is probably going to change very quickly. You've come to a number of 20 kilograms per year. Can you speak a little bit about from where that number came?
Yeah, so...
And just to interrupt you, your point, you might want to also talk to his first point, that it's a historic purchase order.
Yes, so in particular, the US federal government, Department of Energy, we have a purchase order in hand for them that names a price, it names a quantity, it names a delivery date, and it says the helium-3 is coming from the moon. So we believe it's precedent setting.
And delivery by 2030.
Yes, and delivery not next year. So in the future, when we can actually have time to deliver it. So in answer to your second question, so we know as much about the helium-3 market as anyone in the world. Like, we've spent a significant amount of our staff has spent years talking to every customer of helium-3, every current and potential customer. So we have derived demand curves from those interviews. Our 20 kilograms is intentionally constrained not to flood the market. It is intended to basically support the current market price.
Because of time and because I want to allow our next speaker his allotted time as well, I'm going to take the next 3 questions in succession.
I think there's a panel after this in 10:30 anyway. So
yeah, he is on the next panel as well. So let's take the questions, and if anything is not answered here, Gary is also on the next panel.
Okay. So a quick one, Jerry Sanders, NASA. So you mentioned you're looking for partners. Your business case is helium-3. Are you considering any partner for the 6,000 kilograms of hydrogen for every kilogram of helium you extract to sell that commodity?
I mean, we would love to sell that commodity. It is difficult to store. It's also energy intensive. It's energy intensive to keep in a liquid state. It's difficult to store. And we plan to actually use it in a heat exchanger to cool the incoming gas to recover most of the energy that we use to liquefy it. But if there is someone that wants to buy it, we would love to talk to them.
Ben?
Yeah, again, look, just following on from that first question, yesterday we were hearing about the whole issue of non-appropriation and how there's a recommitment to that and the principles that are coming out of this working group, the legal subcommittee working group. What sort of surface area do you think you will need over what sort of time to make your business case? And how does that, do you think, fit into the whole non-appropriation question?
Yeah, so I mean, the surface area had there 1.2 kilometer radius, about 2 to 2.5 kilometer diameter is what we believe we need for that initial capability for 5 years. And in the area that we are in, that we have selected, each of those areas has over 10,000 square kilometers of contiguous area that we could also use. So it's not a huge operation by any means, at least in the near term.
I just wanted to throw in the question of dust. How far does the dust reach beyond that?
Dust
Reach?
I mean, there is no air. So what I didn't talk about in that excavator is it has features in it to reduce the amount of dust. It's a novel type of device which actually the excavation is happening below ground. So it captures and reduces the amount of dust occurring, and it's not going to loft anywhere without an atmosphere on the moon.
So I'm going to take these 3 questions, and we may not have time to answer them. But he's already walking off stage. So you can think about them for your panel. So Danon, and then race to the other 2 questions.
Hey, Gary, looking forward to joining you on the panel here shortly. Sorry, here.
Right.
So when you think about, there's quite a signal from that purchase order, so congratulations on that. And I'm just curious if you could expand on thinking of that volume of helium-3, what the advantages are given the investment in lunar excavation versus, say, terrestrial processes like cryogenic separation or some of those other factors that are also addressing this problem, and how this is sort of the way to go in terms of that demand.
Right, question 1, and then 2 more over here, and you can just ponder these.
Hi, Philipp Reis from the TU Munich. I have a more technical question. So you mentioned on one of your slides that you use mechanical braking to release the volatiles. I was just wondering, have you ever demonstrated that this is feasible, and what would be the yield to be expected with this procedure?
Okay. Yes.
You're keeping these in your mind. And the 3rd question, I think, is Clive Neal.
Clive Neal, University of Notre Dame. Gary, just point out that the numbers you're looking at are using Apollo samples. We really don't know what the helium-3 content of Meteor Regolith is. Prospect Moon is going to get the first in situ analysis of Meteor Regolith for solar wind gases. That's a valuable data set. Have you thought about what you're going to do with that? Because that data set that's either going to make or break your business case, but it's also going to inform the science community about the sun's activity.
Well, on that bombshell, you can take all of those comments to the next panel. Thank you very much, Gary. So I have to be strict with time, sorry. I want to give maximum time also to our next speaker of this session, who is Giulio Marano from the Copenhagen Business School, and is going to talk about PLS SEM analysis and domain-specific NPV approach for lunar oxygen mining missions. Thank you.
Hello, hello. Do you hear me well? Good stuff. So, couple of words about me. Giulio here. I'm currently representing Deloitte from the Copenhagen office. I'm primarily focused at the intersection between finance, innovation, and technology. So, as maybe not many here in this room, I don't come from a technical background, though I'm spending most of my time working with space innovation and stuff. Now, what has been happening in general in the industry in the recent years, starting from, let's say, 2015, is that we have seen an increase in interest of private investors in the space area, which is something that is generally perceived as beneficial because of the dynamics that comes with private investment in terms of agility and the capability of quickly finding innovative solutions. On the other side, what happens is that we have seen, especially in the last few years, an increasing number of non-technical investors. So we had those pioneers funds, thinking of, I don't know, Surfing Space, of some other guys here in Europe. But now we are increasing the number of non-technical investors, which on one side expands the funding base, on the other side brings some misalignment in the understanding of the projects that we are going to fund. So my primary area of focus is making sure that there's an alignment between where the funding is going and the project that we are developing. Now, looking at this study from the OECD, what the general ambitious investors working with deep innovation are struggling with is mostly issues cost related. So when you're looking for high returns, you generally go for high risk, high reward investments, as most of the investments in the space area are. And the challenges are primarily rooted in the cost structures of the projects. Thinking of the long lead times when it comes to payback times, thinking of the large sunk costs when you keep running trial and error processes, and on the other side, the high capex to get started. Similarly, another analysis can be done on what has been done by now in the space industry, and we have a long history of cost overruns and misleading estimations when it comes to large innovative projects. So that is my key area of focus. Now looking at what were the main challenges is that we've been primarily relying on pretty simplistic regression estimates, looking at assumptions that are based on a similar mission, but that falls short when you're looking to something fully disruptive as moon mining or satellite mining could be. What I'm trying to say is that there's not enough data to play with to use the traditional cost modeling. There has been some interesting approaches, especially in the last 10 years, on trying to give a more rounded and, let's say, 360 pictures. Some of the study has been conducted also from the guys here, I'm not sure if in the room, but from the International Space University. For example, the 5C approach that tried to be a bit more well-rounded as an approach, but it's still falling short when you work with something that is deeply innovative. So then what this study has been doing is like looking a bit at what has happened in other industries, thinking of pharma, thinking of other kind of deep tech, innovation industries. And the approach there has been pretty much in the last 10 years of combining, on one side, quantitative analysis, leveraging a bit more the more advanced modeling techniques, and on the other side, leveraging the latent expertise that is lying between the innovators in the field. So what I'm trying to say is there will be no technology that we have not invented, in a way that everything that will be there one day comes from what we've been learning so now. And that's pretty much what the Delphi kind of methods kind of assumes, in a way that you can pretty much leverage the expertise in the people working in the field as a proxy to get to know to a better understanding of where we might be landing on a cost level perception in the future on a new innovative field. Now, to get a bit more details on that, maybe I just move on the next slide. Looking at the approach that has been used, there's a preliminary side which is about identifying what are the key cost elements, and that comes by looking at what happens in the mining industry, talking about, for example, what we're talking here today, which is moon mining, talking about moon missions, seeing the cost modeling for general lenders and all the various mining techniques that has been studied also in different fields. Then after that, there's the involvement of the expert that goes into 2 rounds. The first one is about narrowing and ranking and understanding the relationship between the cost drivers and the various elements. And the second part is about structuring them in a Likert scale, which allows for a larger base interviews structure. Once we're done with those 2, let's say, sessions of interviews and discussions with the experts, comes to the third phase, which is where we go into modeling. what we've been doing here is primarily looking at two models. On one side is the PLSM. This is based primarily on partially squares, and the way it works is that it's primarily successful when you work with limited, let's say, data points, in this case, interview-based data points, talking about 50 to 100 interviewee that we had for this case. And it's pretty efficient when you don't have, let's say, linear and normally distributed estimates, as it is the case for most of the drivers that we analyzed. On the other side, the MPV element is particularly important when we are looking into working with investors, which are interested also in payback periods and, of course, their returns to have such a project in their portfolio. This slide, I would say, is not particularly relevant for this audience in the sense that we pretty much know why it's relevant on one side working with this field. We are all here because we are excited about, in general, what it is mining. What I've been primarily looking at is the oxygen mining component, primarily for in situ utilization with the purpose of working with fueling. What has been explored instead covers a couple of models that were on a technical side promising or particularly interesting when it comes to efficiency and especially technology maturity. On the other side, a little bit of a disclaimer here. The study has been based on these two models primarily, so the one coming from the Polaris studies and the one on sublimation and electrolysis published in 2018. But the same kind of approach and the same kind of equation can be equally used on any other model, which means also if we want to look at the same study for helium-3, for example, it can be easily replicated. So now going a bit more, looking at the two models for the last minute. The first part is about the PLSM. It works that we identify 14 cost drivers, some direct, some indirect, and what the PLSM gives is an analysis of the relationship, how those cost elements influence each other, and there's some latent factors that are unveiled by this way of modeling, and there's some direct and indirect factors. So the importance of having a PLSM model is about identifying what are the drivers and the key impact factors. So what can be seen here is, for example, what are the key focus areas and what needs to be solved first in order to allow a mission in the future. Now, some of the findings of this model has been also employed in the second part of the research, which is the MPV modeling. Here I need to thank a study that has been done 25 years ago, something like that, which was a preliminary study on the mining on satellites, so not necessarily on the moon, but these studies here has been basically renovating and adapting kind of the function for a moon case. The findings here are more looking into what would be the required upfront investment to have a return in a given number of years. And here it pretty much identifies what are the requirements, what are the elements that weights more when it comes to making sure this kind of project can come to life in a short term. Leaving the last minute for the findings, or like basically what this leaves us with is the current technology or the current model that has been used are allowing us to build some sort of a model that allows us for having oxygen on the moon for a cheaper price than would be bringing it from Earth. But this requires like an upfront investment, which will be too heavy to be bared. Basically, even if we combine ESA and NASA budget together to have that happening in 1 or 2 year time, meaning that we are too far for having such a project landing on the floor. Now, what the model is particularly interesting with is that we have the PLSM part that allows us to understand better what are the drivers. So, for example, one thing would be the storage. That is a huge bottleneck. The other thing would be also on the rapidity of reprocessing. And the MPV instead points us towards considering what would be an ideal payback period, an ideal timeline for running these investments. Now, beyond that, what is particularly interesting for this study is that it's not that much about the project itself, but it's that it can be easily replicated on any other study when it comes to making prediction when you don't have historical data to play with, which is pretty much the general issue that we have when we work with space innovation. Yes, thank you very much for listening.
Thank you so much, Giulio. Any questions for Giulio? Ah, yes, we have question, hand up in the middle, right in the middle. If you keep your hand up, the microphone can find you.
Thanks. Hi, Michel Carnet from Imperial College London. So I'm
Hello.
wondering, in your model, and that's great, I think we really need that line of work now. How do you guys account for uncertainty and risk in the economic modeling?
Yeah, so there's a discerning element there. So on one side, there's the technical kind of risks. On the other side, there's the risk associated with the markets. So let's say working more on market demands and the general condition around that, right? And we model in two separate ways. So on one side, there's the technical part, and that's pretty much derived by analogies on similar studies or similar experiments that are currently running, either landers for the moon or, for example, other mining techniques also on Earth. So there's a part on that, and it's pretty much parametric analogies with other missions. The market side instead is based pretty much on the market forecast and market prediction that are being run in the last few years, also by my own firm, for example.
So the modeling itself is not necessarily stochastic. That's what I'm asking.
No, it's not stochastic. No,
All right,
exactly.
thanks.
Yeah,
Let's have a chat.
of course.
We have a question in the front row. Maybe it can be thrown across gently.
Aaron Shalmetzi. My question is, did you consider if technology developed for ISLU possibly can be reused on the Earth, and if it's how it's affecting the costs? Did you take consideration like this?
So the study was based for in situ utilization.
Yes.
So there has been no consideration on bringing back to Earth, basically, any of the material. So
just the technology I meant, not
no,
necessarily the
no,
material.
it has only been focused on the development related to the in situ utilization.
Mm-hmm.
You can account for other uses on the moon, but not to bringing back the technologies. The downstream, basically, implication of the technologies has not been accounted in the cost model, no.
Okay, thank you.
Thank you. So we have another question at this side of the room, and then I can see a hand up at the other side of the room. If you keep your hand up, then we can find you more easily.
Jonathan Slavic, Astrobotic.
Yes.
So for this model looks fantastic, but you have a lot of technical inputs going into the model, and I think if you ask 5 different subject matter experts in this room, you'll get 5 different answers. How are you validating the inputs to this model from a technical perspective?
So this is exactly the point of working with what you would call a strategic foresight kind of area, and where Delphi technique is based on. So the idea is that the later knowledge is kind of scattered and shared between the experts. So we've been working with people that have startups in the space mining area, working primarily with satellites. We've been working with people from the Artemis program, working on moon landing, especially in the southern hemisphere. So there's, of course, some discrepancies that we analyzed when we come to the straight answers from the interviews. The idea of working with PLSM is that it filters out part of those discrepancies and trying to find a medium. And that is pretty much what the idea is behind. So trying to not leverage and let's say, emphasize one perspective, but trying to use the shared knowledge and the collective knowledge as a proxy for innovative technologies.
I thought we had a question here.
Hello, Melchior Conti, Space Resource Engineer at ESA. You said that you are not considering returning products. That's fine.
Mm-hmm.
So are you considering only customers on the surface? Because there is a big engineering effort in trying to create refueling station in various spots in space between Earth and Moon.
Yeah, so refueling is the, I would say, 90+% of the case that we considered.
No, but off the surface of the Moon, without returning, but in various locations in space. Do you consider that in your model?
We consider only refueling on the Moon.
Okay, thank you very much.
Thank you, Melchior. Okay, thank you very much, Giulio. Thank you. Thank you for your talk, and thank you for this session.